All right, so let's start out with any questions. Okay. Something I guess we need to sort of talk about briefly is that in case the school does get shut down because of some highly communicable disease, expect just loads of videos being produced. If you've seen my videos, you know how fancy my graphics get, so it'll probably be on par with that, since I don't have a whiteboard at home. I'm still expecting at least we've got a couple weeks before we have to worry about that, but the doomsayers say it's coming.
How likely is that?
Well, I mean, considering it's, as the past couple of days, a couple more states picked up their first case. Because the last chart I had seen was Texas was as far east as it's gotten, but now there's Florida, Vermont, New York, New Hampshire, as of yesterday.
And Georgia. I saw Georgia yesterday.
I had not seen Georgia yet. So, oh boy.
Wash your hands.
Yes. And even if the virus weren't coming, you should still wash your hands.
That's sound advice.
All right, and on that upbeat news, at least when you die from physics, you know it's pretty quick. There's none of this slow, drawn out thing. And also good news for you, apparently the people under 30, has anyone under 30 died yet? I think it's primarily old people.
I think it's old people and infants.
Actually, I heard that no kids had died.
Oh, really? I heard it affected the young kids and old people the most.
I heard it affected.
But
That's tradition, but so I heard speculation that it's close enough to the cold virus that since kids get a lot of colds, that they have some sort of immunity built in.
Mhm.
Whereas adults, it's been too long since, I don't get colds as often as I used to.
Yeah, like once a year.
Or maybe it's just all hooey and it's, it's pundits trying to hit talking points. All right, segueing that into apparent depth. So I have an object here under the water, and as light hits it and bounces off and then smacks you in the eye, as it's coming up from one area to another area, I am going to assume, for the sake of this drawing, that N2 is less than N1. And therefore, as it hits, it's going to bend away from the normal, the perpendicular line right here. Hitting a couple of, labeling some points here. So I'm going to label this as, those are supposed to be dots right there. This is point O for object, this is I for image, this is A. And this point right here is B. B is the point directly above where the object is on the surface. Any questions about the notation that I have right here?
What is the eye again? Is that the image?
Yes, that's the image. Since we sort of, our brain process is assuming that, things, if we're looking straight at something that we assume is right in front of us. So thus, it's an extension of this line right here hitting us in the eye. So if I look at the triangle OBA, so I'm looking at the triangle from here to here to here. Well, I've got this vertical right here and I have a vertical right here. So from point A down to point B down, those are parallel lines, and it's cut by a transverse here, this line going from O to A. And so the alternate interior angles are congruent. So this angle right here is also theta 1. This angle, theta 1. So this angle here and this angle here are the same. This distance between point A and point B is D. And my hypotenuse, how did I label that? No, I just left it generic. So the sine of theta 1 is just going to be the opposite side over the hypotenuse, just whatever this distance right here, which I'll signify as the measure of AO. So the measure of AO is just that distance right there. We can look at the other triangle, so where I is the vertex, so basically IBA. Again, if we look at the geometry of it, I know this angle right here is theta 2, because I labeled it as theta 2. And that would be congruent to this angle right here, theta 2, which would be congruent to this angle right here. So this angle right, that is drawn, that's one of my worst drawings right there. And that has competition. That's supposed to be a right angle there. Right angle. So this angle right here is my theta 2. The distance between A and B is still D, that hasn't changed. And so we have the sine of theta 2 is equal to the opposite over the hypotenuse, D over the measure of AI. So this is just straight up geometry. Presumably bringing back some really fond memories. But for those for whom it is bringing back fond memories, don't worry. We're going to have even more geometry coming up after this one. Woo! Now from Snell's law, if I look at the relationship between theta 1 and theta 2, I know that N1 sine theta 1 equals N2 sine theta 2. Snell's law, that's what we derived yesterday. And so I know that sine theta 1 over sine theta 2. So I'm bringing theta 2 over there, so I have to bring N1 to the other side. It's going to be N2 over N1. Which, using these relationships we had just right here, is equal to D over the measure of AO over D over the measure of AI. Now, this would then come out to be the measure of AI over the measure of AO. So in other words, the distance from the top one is the image from the image to the point where the light hits the surface over the distance from where the object is to where the light hits the surface. Let that sink in and feel the full weight. So that's pretty much as far as we can take it without having to make an assumption here. Now the textbook does make an assumption at this point. They assume that you're looking at an object that's far enough underwater that this angle right here and this angle right here are small. That you're not looking at it from an angle like that, but you're looking at it more down like this. So if we could make that assumption. In other words, if theta 1 is much less than 1, and theta 2 is much less than 1. Again, when I've drawn this up, notice there are no units next to the 1. Therefore, what are the units of this?
Radius?
Yes. And so I'm dealing with a small angle here, and therefore we use
Small angle approximation.
right on. So we have the small angle approximation. So in that, if I look at, let's just say the ABO triangle right here, the tangent of theta 1 would be the opposite over the hypotenuse, which is the measure of AO. That's approximately equal to the sine of theta 1, which is equal to, oops, got that backwards. That first one should be sine, this one should be tan. The tangent of theta 1, which is opposite over the adjacent, so that's d over this length right here from B to O, which is just P. Therefore, using the small angle approximation, we see that the measure of AO is approximately equal to just whatever the depth is of the actual object. Go through a similar argument, and we can show that the measure of AI is approximately equal to the depth of the image. And so this becomes Q over P. So the ratio that the book settles on is the ratio of the index of refraction is equal to Q over P. Just want to at least go through that, not that you couldn't necessarily follow it in the book, but I just wanted to display it. Questions about the beautiful nature of this derivation?
What does M stand for again?
Measure. Technically, from a geometry point of view, AI is a line segment, and what we care about is the length of it, so it's the measure of the line segment, or length of the line segment. Apparently you've forgotten, or they don't use that notation in geometry anymore, or you never took geometry.
I don't think they use it anymore.
Okay. My day.
Archaic.
Just like art.
Then this is exposure. So next time you're talking to your parents about geometry, and they bring out the measure, you go, yeah.
I've seen that before.
They're not that educated.
We'll need to assume they'd remember.
Probably one of my big public nerd moments was I don't think I was married yet, I think I was just dating my current wife at the time. But we were in a restaurant that had crayons and paper for the tablecloth so you could write on it.
Mm-hmm.
And she was teaching also at the time, so we would go trig all over this. And then one of my students shows up. Naturally thinks this is what I do. All right, any questions before I erase this? And we do the next great geometric derivation. This one's in the book, the next one is not. All right, I need to write stuff down here. All right, so I need my lens. We're going to derive, this is the lens maker's formula. So I'm going to establish first we have sort of our central axis here. Let's see, I want a lens. That is drawn horribly. I probably should draw my lens first and then draw my central axis. Sorry, I want to try to draw it as accurately as possible because I think it's going to be easier in the end to sort of follow why I've drawn the lines where I've drawn them. Attempt to be a little bit attentive here. That looks a little bit more central. I have definitely drawn the two sides of this lens to be significantly, noticeably different radiuses. So if I have a starting point over here, so light coming in, this is point P. So a light beam coming in, hitting this, we do have an index of refraction, so I would draw something tangent to it. Now, in the past when we've done the index of refraction, I think I did some of this yesterday, but when we first did Snell's law, we had a very flat surface. The light hit it here and then went into another surface at a different angle, or another medium. Here, when we have a curved surface, we have to draw a tangent line and sort of treat that like a flat surface. And so this is coming in at a certain angle. We assume that the index of refraction of this is greater than here. We're going to just go ahead and make this air on the outside here. And the index of refraction is approximately equal to 1. Index of refraction is approximately equal to 1. And the index of refraction here is not 1. Probably 1.5, 1.6 if we're talking about glass, and then plastics have various indices of refraction. It depends on for what you're actually making the lens. So when it hits this, it's going to bend. So this has some initial angle here, and just to keep straight in the notes, this is angle theta 1, and then this angle right here is theta 2. And this is going to cruise along, and it's going to hit that. And when it goes into air, it's going to move away from the normal. So let's draw the normal here. So this angle here is theta 3, and then it's going to bend away from it. This angle here is theta 4. So light, now generally when dealing with a thin lens, we treat it as it comes in, it goes out. We don't worry about the bending within the lens itself. It's sort of implied in the stuff we do for thin lenses. But for something like this, we do care about what's happening inside the lens in terms of the derivation. Marking the points, that's point P there, this is point A. This point right here is point D. This line right here is going to hit down here at point E. That's supposed to be straight. This line right here. Yeah, dust cross. All right, so I have P, E, this is point Q, this is point C, and then if I extended this line right here, this is point B. I give people a chance to catch up and also ask questions about what the lines mean before I start adding angles, other angles. Double check, make sure I've got it. QCD, AD. All right, so if my object is at point P down there, then my object distance, which we've used as DO in the past, is the distance from here to, well, in essence, somewhere around here. So we have this distance of d sub O. And the image distance, well, this is where the image shows up, so the image distance is going to be d sub I. If it's a thin lens, then DO plus DI should just equal the distance from P to Q. But we are taking into account that this lens does have a thickness to it. We will assume that it's a small thickness at some point, but for right now, I want to distinguish that from here to here. And then the height, where this light beam hits up here, this is H sub O for object, and the image, we'll call this H sub I. Actually, in keeping with my notes, H sub 1 and H sub, I have 3 here. Okay, make it 2 later on. Let's confirm. For some reason, I call it H sub 3. And I think two other distances. The distance from point D to E is R sub 2. That is the radius of curvature of the backside of the lens. The distance from A to C, that's the radius of curvature of the first side of the lens, of side 1. So this is R sub 1. So sort of writing that out. ED is the radius of curvature of side 2, and AC is the radius of curvature of side 1, this being side 1, side 2. And now the angles, let's go for a different color just for fun effect. This angle down here, I'm going to label as alpha 1. This angle here, beta 2. Then over here, alpha 2, beta 1, and gamma, although, yeah, I do use gamma. And I think now we have labeled, it's time to do some algebra, geometry. What do you know about the angles in a triangle?
They-
180.
All right. What do you know about the angle of a straight angle?
That's a 180.
All right. So if I have a triangle like this angle, what is the relationship of this angle right here to what I have inside the triangle? All right, let's do real numbers here. So if this is 30, 50, and 110, obviously not drawing to scale. Let's draw something more, use numbers that are more realistic here. So let's make that 80, 50, and something different there, 60. 80, 40, and 60. What is this angle right here?
40.
All right. All right, so we have, all right, so equation 1, first off, we have the light going in from the air into here, and so we have a relationship between those two. I know that N1, or 1, times the sine of theta 1 is equal to N times the sine of theta 2. Snell's law. This is equation 1, we'll make reference to it later. Equation 4, just to keep track in leak with my notes. If we do the same thing over here, I know that n times the sine of theta 3 is equal to 1 times the sine of theta 4. And again, the 1 comes from the index of refraction of error. It's close enough to 1. Equation 2 is looking at, we got theta 1, alpha 1 plus beta, yeah. So looking at this triangle, PAC. So if I look at PAC, this angle here is theta 2, this angle here is alpha 1, this angle here is beta 1. So again, PAC. Then by what we just did over there, I know that theta 2 is equal to alpha 1 plus beta 1. And so this comes from PAC, triangle PAC. If you look at triangle ACB, so AC and possibly, oh, there we go, B over there. So looking at that stretched triangle right there. ACB. This is gamma. And this is theta 2. And this angle over here is beta 1. We'll label this equation 3. We have beta 1 is equal to theta 2 plus gamma. Lisa?
For the PAC triangle, it
Yes.
says where you have angle 2, how is that angle 2?
Oh, that should be theta 1. Thank you. Is that cleared up? Ish. We're looking at this, so since A is here, and this is coming straight off of it, this line right here is connecting C and A. This line right here connecting C and A. And theta 1 is between that line and the line connecting P and A. So that's why that's theta 1. Apologize for the bad subscript. Two more equations and then we start doing some math, some algebra. Equation 5. Looking at triangle DEQ. So we got D, E, and Q. So D is here, E is here, and Q is there. I know that this is alpha 2. This angle right here is beta 2. And then the line that connects ED and DQ, we have this angle here of theta 4. And so theta 4 is equal to, well, first alpha 2 plus beta 2. So very similar to what we did on the other side, we're just doing it on the right hand for side 2 now. And then the last triangle is DEB. It's going to give us our equation 6. So DEB, so looking at that long skinny triangle there. So this is E, D, and B. And theta 3 is what's between, we have this line connecting D and B, and the line that connects D and E, the angle between that is theta 3. And this angle here is beta 2, and this angle here is gamma. And so we have theta 3 is equal to theta 2 plus gamma. And that's supposed to be a beta there, as opposed to a gummy bear in the heat. Speaking of which, any of you taken a gummy bear in the summertime or when it gets hot, like the back of it to stick to your rear view mirror?
No, can't say that, no.
If it's really hot, that thing's gonna melt and fall right into the gear shifts. But if it's warm enough, it'll start to sag, and at first it starts like a gummy bear, and then it's sort of a fat gummy bear, that's, you know, sort of pear-shaped, then it becomes a gummy Buddha, and then a gummy raindrop, and then gummy snot, and, you know, just you get this long string. It's called science. So when your significant other asks why you have a gummy bear stuck to your rear view mirror, it's science. All right, I think we are now ready to do some algebra. So for geometry fans, I apologize, we're gonna get away from geometry for a little bit here. But for algebra fans, you are in luck. There we go. Let's get rid of the triangles. Let's see if I can cram this into the space we have here. So first thing I'm gonna do is I'm gonna take equation 2 and equation 3, and I'm gonna plug it into equation 1. So I'm gonna take 2 and 3 and plug it into 1. Because I have theta 1, which I can plug into here, and I have, theta 2, which I can plug into there. There is one other assumption that I obviously need to make here. Oh. Yeah, and the one other assumption, of course, because it's physics, the small angle approximation. We will assume that the system is coming from far enough away that theta 1, theta 2 are much less than 1. And so our equation 1 becomes theta 1 equals in theta 2. Equation 2, we have alpha 1 plus beta 1. Alpha 1 plus beta 1 is equal to n times theta 2, which coming from equation 3 would be beta 1 minus gamma.